Welcome to our quantum deep dive. You know, in the world of AI, we're kind of running up against a wall, a computational limit to how well our machines can really, truly understand us. But what if the solution isn't just about building bigger computers, but using a completely different kind of physics? Well, today we're diving into a concept that could completely rewrite the future of artificial intelligence. It's called quantum named entity recognition, and this whole deep dive is based on a fantastic essay by Georg Owe Schneeplot.
So here's how we're going to tackle this. We've broken it down into 6 key parts. We're going to start with the AI you're already using every single day, maybe without even knowing it. Then we'll look at where it's falling short, and from there, we'll jump headfirst into the pretty weird and counterintuitive world of quantum mechanics to see how it might just hold the key.
All right, so first up, let's talk about a piece of tech you interact with constantly, even if you don't recognize the name. Named entity recognition, or NER for short. Honestly, you can think of it as this invisible engine humming along in the background of so many apps you use.
At its heart, NER is all about teaching computers to read a chunk of text and, spot the important stuff, the nouns, and then sort them into the right buckets. So picture this. You've got the sentence, Apple announced a new iPhone in California. An NER system would instantly flag Apple as an organization, iPhone as a product, and California as a location. It seems simple, but this is the absolute first step for a machine to actually comprehend what it's reading.
And you really do see this everywhere. It's that little bit of magic that helps your search engine figure out you're looking for the company Apple, not the fruit. It's what lets your virtual assistant know who or what you're asking about. And in really specialized fields, like medicine, it's a complete game changer. It helps researchers find every mention of a specific drug or disease across millions of papers in just seconds.
Okay, but here's the thing. For all its power, classical NER is starting to hit a wall. A pretty hard one, actually. As all our data gets way more complicated and the questions we ask get more nuanced, the old ways of doing things are really starting to show their age.
I think the biggest headache is just plain ambiguity. I mean, context is everything, right? Classical models can have a really tough time figuring out if Amazon is the retail giant or the rainforest without a ton of extra data to help it. Same thing for Apple. Or how about the word Stark? Is that a family name from a TV show, or are you just describing a really severe, bare landscape? For us, it's pretty intuitive. For a computer, it's a huge problem.
And this is the great irony, right? The very models that make NNR so powerful today, these huge transformer models like BERT, are also its biggest weakness. They require just an insane amount of computing power. They're incredibly hungry for data. We're talking millions of examples, and they just don't adapt well. If you train a model on news articles, it's going to fail, and I mean fail spectacularly, if you suddenly ask it to read legal documents. We are just hitting a computational wall.
So if our classical computers are stuck in a rut, where do we possibly go from here? Well, researchers are turning to a totally different way of thinking, quantum computing. And look, this isn't just about making a faster chip. This is about using a completely new set of physical laws to compute. Okay, so here's the fundamental leap. The computer or phone you're using right now runs on bits. And a bit is just a simple switch, right? It's either on or off, a 0 or a 1. That's it. A quantum bit, or a qubit, well, that's a whole different ballgame. Thanks to the truly bizarre rules of quantum mechanics, a qubit can be a 0, a 1, or, and this is the crazy part, a combination of both at the very same time.
This mind-bending idea is called superposition. The best way to think about it is like a spinning coin. While that coin is in the air spinning, it isn't heads or tails. It's kind of both at once. A qubit basically holds that mix of possibilities mathematically. And this isn't just some cool party trick. It's the key that lets quantum computers check out a huge number of possibilities all at once, in parallel, which gives them the potential for a massive speed-up.
And superposition is just one tool in this wild toolkit. You also have something called entanglement. Einstein famously called it spooky action at a distance. This is where two qubits become linked, almost mystically, no matter how far apart they are. If you measure one, you instantly know the state of the other. It's just wild. Then there's interference, which is a clever trick quantum algorithms use to basically cancel out the wrong answers and boost the chances of getting the right one.
Okay, so we've got all these strange, almost sci-fi quantum rules. How on earth do we actually apply them to a real-world problem like understanding human language? Well, this is exactly where quantum named entity recognition, or QNER, comes into the picture. We're starting to move from pure theory to something much more tangible.
And as Schneppet's work really points out, the core idea here is to use that natural parallelism you get with quantum mechanics to model all the messy, complex, context-heavy relationships in language way more efficiently than we ever could before. So instead of chewing on one possible meaning at a time, a quantum system could, in theory, explore a huge range of contexts all at once.
Now look, pure large-scale quantum computers are not quite ready for prime time. So the most promising path forward right now is a hybrid approach. It's really the best of both worlds. You let a powerful classical model like BERT do what it's great at, all that initial heavy lifting of turning words into meaningful numbers. Then, you encode that rich information into the quantum states of your qubits and hand off the really tricky classification job to the quantum processor to let it work its magic.
This all sounds incredible, because, well, it is. But now it is definitely time for a reality check. We have to ground ourselves here, because building a useful large-scale quantum computer is easily one of the hardest engineering challenges humanity has ever taken on. And we are just not there yet. The reality of today's quantum hardware is that it's noisy, it's small-scale, and it's unbelievably sensitive. You have to understand, qubits they're divas. They are so fragile that the tiniest vibration or the slightest change in temperature can make them lose their special quantum state. That's a process called decoherence, and it completely wrecks the calculation. On top of that, we just don't have enough of them yet, and we don't really have the right kind of data to train them with. So, with all these huge roadblocks, you might be wondering, how do we ever get there? How do we move from this NISQ era, that's a term the physicist John Preskill came up with for noisy, intermediate-scale quantum computers, to a future where something like QNART is actually a practical tool people can use every day? Yeah, the road ahead is definitely a marathon, not a sprint. But the really amazing thing is that the pace of progress is picking up fast. Right now, the focus is on two tracks running in parallel. One is just building better, more stable hardware. And at the same time, the other track is all about developing smarter hybrid algorithms that can actually squeeze useful answers out of the imperfect machines we have today. Hardware companies like IBM have put out some really ambitious roadmaps. Right now, we're in this NISQ era with chips that have maybe a few hundred qubits. The next big milestone is to get across that 1,000 qubit threshold in the next few years. But the real holy grail, the long-term dream that everyone is chasing, is fault tolerance. Building systems that have such good error correction that they give you perfectly reliable results every single time. And this chart really shows you why everyone is chasing that goal. The potential payoff is just enormous. The hybrid models we're working on today could give us a really significant boost for certain problems. But a fully realized fault-tolerant QNAR system, we're talking about an exponential speedup. That's not just a little bit better. It would fundamentally change the entire economic landscape of what's possible with large-scale AI.
So, to wrap this all up, quantum named entity recognition is not science fiction anymore. It's a very real, very active field of research that's trying to smash through the limits of today's AI, not with more brute force, but by actually harnessing the fundamental laws of the universe. The challenges, as we've seen, are absolutely immense. But that drive to create faster, smarter, and more deeply context-aware AI is an incredibly powerful force for innovation. And it leaves us all with a pretty fascinating and kind of mind-blowing final question. As we build these totally new kinds of machines, will this new form of computation ultimately change our very definition of what intelligence even is? This deep dive was based on the work of Jorgo A. Schneppet. For more on this and other quantum explorations, you can visit his website at schneppot.de.
Thank you for joining us, and goodbye.
Schneppot.de is a private project by Jorgo A. Schneppot dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.